So this is the problem statement for design of circular water tank with fixed base and tank resting on ground. We will be designing this by IS code method. Problem statement is design the water tank of a circular water tank, wall of a circular water tank 7 meter diameter and 4 meter in height. The tank is resting on the ground and sketch the details. This is the problem. So first we will find take out what is given data. So given data is that the given data is the diameter of your water tank is given. So we have diameter D is equal to 7 meter. Height of water in the water tank is given as 4 meter, and we have to design the wall of your water tank. Okay, for designing the wall of your water tank, okay, first thing we should finalize what is the minimum grade of concrete we will be using. So let us use grade of concrete. M30 grade of concrete and Fe415 HYSD steel. Okay, we'll be using these two grades of concrete and steel. Now we have to find out the values of different permissible stresses. Let us consider value of sigma CBC. Okay, this will be given in IS 3370. This is given in IS 3370. Also I have taken this out here. Okay, so for M30 grade of concrete, you can see here, for M30 grade of concrete, the value of sigma CBC, these values are given in IS 3370. You can see here the value of sigma CBC is 10 Newton per mm square. Okay, so we'll take sigma CBC is equal to 10 Newton per mm square. Okay, so we got first value. Then we have to calculate the value of sigma BT. Okay, we have to calculate the value of sigma BT. This value is again given in this table permissible compressive stresses. Okay, here you can see here for M30 grade of concrete, okay, okay, so these are the values of permissible stresses. Okay, uh, for M30 grade of concrete, the value of sigma BT for M30 grade of concrete, you can see here the value of sigma BT is given as 2 Newton per mm square. The next value we have to find out is value of sigma CT. Okay, this is sigma BT. Okay, we have to then find out the value of sigma CT. Okay, that is the permissible tension stress in concrete in direct tension. Okay, so this is the value of sigma CT. So for M30 grade of concrete, you can see here it is given as 1.5 Newton per mm square, and the last permissible stress, that is sigma ST. We have to find out the value of sigma ST. So what is the value of sigma ST? That is given in this particular table. Okay, you can see here for the value of sigma ST, that is taken as 130 Newton per mm square. This is taken as 130 Newton per mm square. Okay, so this is how we will be finding out the values of different permissible stresses. Okay, we'll just write down these values here. Okay, so we have got this sigma CBC is equal to 10 Newton per mm square. Then we have sigma BT is equal to 2 Newton per mm square. All these tables are given in IS 2370. Okay, sorry, 3370. Then sigma CT, this is equal to 1.5 Newton per mm square. and sigma st is equal to 130 Newton per mm square. Okay. Okay, now we have to calculate the values of different design constant. Okay, this is we will be designing considering the your working stress method. So for that working stress method, we have to find out the values of design constant. So step number one, design constant. Okay, so we have different design constant in your working stress method. The first one is modular ratio m. Okay, so this is modular ratio m is equal to, the formula for calculating modular ratio is 280 divided by 3 sigma cbc. This formula is given in IS 456. Okay, so this is equal to, we have 280 divided by 3 sigma cbc value is 10 Newton per mm square. So write down here 10 Newton per mm square. Okay, so we'll get this value is equal to, modular ratio is equal to 9.33. okay, 9.33. Then second design constant is value of k. Okay, so k is equal to for calculate the formula for calculating this value of k is equal to m into sigma cbc divided by m sigma cbc plus sigma st. Just put these values. We have m is equal to 9.33. we just calculated that value, multiplied by sigma cbc was 10 Newton per mm square, divided by again m, that is 9.33, multiplied by sigma cbc is 10 plus sigma st is 130. So we get this value of k, this is equal to 0.416. Then another design constant is there, that is j. Another design constant is there, that is j. This is given by j is equal to 1 minus k divided by 3. So this is equal to 1 minus value of k is, we have calculated 0.416 divided by 3. So we get the value of j is equal to 0.86. We get the value of j is equal to 0.86. Then next constant is r. Sometimes it is considered as capital Q. Okay, we will be considering it as a r. Okay, just a minute. Okay, next design constant is capital R. So we have r is equal to, the value of r is calculated by this formula, 1 divided by 2 into sigma cbc into k into j. Just put the values 1 by 2. We have sigma cb is equal to 10 multiplied by value of k is 0.416 multiplied by 0.86, that is j. So we get the value of r is equal to, this r is equal to 1.78. okay, so we have got this m is equal to 9.33. the value of this k was 0.416. then we have j is equal to 0.86, and finally r, we have got this value r is equal to 1.78. Okay, now we have to find out the value of thickness of your water tank. Okay, so step 2, thickness of water tank. water tank wall. Okay, so the thickness of water tank wall will be considering, let us consider the formula. Thumb rule is H is equal to T is equal to 30 into H multiplied by plus 30H plus 50, where H is in meter. So we have H is equal to 4 meter, that is height of your water tank. So 30 into 4 plus 50, so this comes out to be 170 mm. Let us assume that will be considering T is approximately equal to 200 mm. Okay, let us take thickness of water tank wall is equal to 200 mm. We have H is equal to 4 meter, we have diameter is equal to 7 meter. Okay, therefore now we have to calculate the values of different bending moment and coefficient hook tension. So step number 3, calculate bending moment. Okay, now for calculating the bending moment, first thing we have to calculate is, we have bending moment, this is equal to coefficient multiplied by gamma h cube. This is the formula. Now we have to find out the coefficient value. Okay, so coefficient can be calculated by using the tables given in IS 3370 part 4. Okay, so coefficient, for calculating that coefficient, we have to first find out the value of this. We have to first find out the values of h square upon dt. Okay, you can see here in this particular table, you can see we have to first find out the value of h square upon dt. So h square upon dt, so this is equal to, we have h is equal to 4, so 4 square divided by d is 7 and multiplied by thickness is 0.2. So we get the value of h square upon dt, this is equal to 11.4. Okay, we have got the value of h square upon dt 11.4. Go to this table which is given in IS 3370 and find out the coefficient for bending moment. This is the table for bending moment coefficient. Okay, we have got the value of h square upon dt as 11.4. so the coefficient is in between these two values. Okay, so just find out which is the maximum coefficient. You can see here, okay, so the coefficient for bending moment will be somewhere between these two values, that is this 10 and 12, because our h square upon dt is equal to 11.4. so find out where the maximum coefficient is there. Where is the maximum value of coefficient? You can see here the maximum value of coefficient is this, that is 0.0122, okay, and 0.0104. okay, this is the maximum value of coefficient. So just interpolate using these two values of 10 and 12 and minus 0.0122 minus 0.104. so we get the value of coefficient. After interpolation, we'll get the value of coefficient is equal to minus 0.0117, so this is the value of coefficient we have to use. Okay, so coefficient will be, okay, so for okay, so bending moment coefficient for 10 it was minus 0. For 10 it is, where for h square upon dt value of 10 it is minus 0.01, into, yeah, and for h square upon dt value of 12, it is minus 0.0104. Okay, so for h square upon dt, h square upon dt is equal to 11.4. We get bending moment coefficient, bending moment coefficient, this bending moment coefficient, this will be equal to minus 0.0117. So we have got the bending moment coefficient. We have bending moment formula for calculation of bending moment. M is equal to, we have bending moment is equal to coefficient multiplied by gamma h cube. Gamma h cube, we have coefficient is equal to this value, that is minus 0.0117, so minus 0.0117 multiplied by gamma h cube, that is gamma is 10, let us consider 10, or we can also take 9.81, 10 into 4 cube. So we get this bending moment value, m is equal to 7.5 kilonewton meter, sorry, okay, 7.5 kilonewton meter. This formula is taken from IS 3370 part 4 1967. Okay, so this is how we have to calculate the value of bending moment. So we get this value of bending moment. For now what we have to do, we have to check whether this thickness we have assumed, that is 200 mm, is sufficient or not. Okay, so step number 3 will be, step number 4, check for depth. Okay, we have to check the depth or thickness, okay, T. Okay, so we have T, formula for checking this is T is equal to under root m divided by r into b. Okay, so we have m is equal to T required. Okay, this will be T required. So we have m is equal to 7.5. We will be neglecting this negative sign, because this particular negative sign, it indicates that tension, this tension is on inner side of wall. Okay, so we will be neglecting this negative sign here. Okay, so this will be equal to 7.5 multiplied by 10 raised to power 6, we are converting it into Newton mm. Okay, divided by, we have r, we have already calculated the value of r as 1.78 multiplied by b, width of your wall, let us consider it as a 1000 mm. This is standard we will be considering. So thickness required, just solve this, we will get thickness required is equal to 65 mm. Okay, but as we have provided, T provided is equal to 200 mm. Okay, so this is greater than T required of 65 mm. Okay, and hence, okay, hence the thickness we provided, it is okay. Okay, now next step is step number 5 to calculate the hoop tension. Okay, so step number 5, is calculate hoop tension. To calculate the hoop tension. Okay, okay, so we have to now calculate the value of hoop tension. Okay, we have to calculate the value of hoop tension. Now we know that the hoop tension is calculated by this particular formula, that is hoop tension T. This is equal to, the formula for calculating this hook tension is equal to coefficient multiplied by gamma HD divided by 2. This is the formula for calculating the hook tension. Already we have calculated the value of h square upon dt. We have already calculated the value of h square upon dt is equal to 11.4. 11.4 is the value of h square upon dt. Okay. Okay, that is equal to 11.4. That is equal to 11.4. And now these values are known. Okay, these values are known. Only unknown is this particular coefficient of hook tension. Okay, so for calculating this value of coefficient, again we have to go to this IS 3370 table number, IS 3370 table number 9. Okay, here you have to find out at which value of h square upon at which height the value of h square upon dt will be the coefficient is value of coefficient is maximum. So we will be using this particular table which is given in the book itself. Okay, you can see here for 11.4 value it will be between these two values. So maximum value of coefficient that will be in between these two values. Okay, you can see here this is you can see here the value of maximum coefficient will be between these two values, that is 0.608 and 0.628. so for 10 we have coefficient 0.608 and for 12 the coefficient value is 0.628. so we have to calculate the value for 11.4. okay, so that can be calculated by using our interpolation. So just go for interpolation, you will get the value of coefficient. Okay, you will get the value of coefficient is equal to 0.622. 0.622. Therefore this particular equation t is equal to, this becomes t is equal to coefficient is 0.622 multiply gamma as 10 multiplied by h is 4, height is diameter is 7 divided by 2. so we get the value of hoof tension. This is equal to 87.08 kilonewton. 87.08 kilonewton. Okay, and we'll directly calculate the value of steel required, AST required for this particular hoop tension. Okay, we will be first calculating the AST required for hoop tension. This AST required will be equal to, formula for calculating the AST required is T divided by sigma ST. T divided by sigma ST. Okay, so this is equal to, just put the value, this value 87.08 divided by sigma ST. We have already taken the value of sigma ST as 130 Newton per mm square. We have taken this value from table given in IS 3370. Okay, so this is equal to AST required. This will be, okay, we have to convert it into Newton, so multiplied by 10 raised to power 3. Okay, so this will be equal to, AST required is equal to 670 mm square. 670 mm square. And we have to check whether this is more, this value of AST required is more than AST minimum. Therefore we have to again calculate AST minimum. We have to again calculate AST minimum. Okay, we know the value of AST minimum given in requirements of water tank, which is given in IS 3370 part 2, that minimum AST shall be 0.35% of area of surface zone. Okay, so AST minimum is equal to 0.35% of area of surface zone. Okay, so this is equal to 0.35 divided by 100, because it is 0.35%. okay, multiplied by, okay, 1000, this is width, multiplied by the depth. Okay, now how we have to take the depth required? Okay, that is given, you can see here in this particular figure. Here in this particular figure you can see if the sorry yeah, here you can see here, if the depth or thickness of your wall, if the thickness of your wall is less than 500 mm, yeah, you can see here in this particular figure, if the thickness or depth of your water tank wall or base wall is less than 500 mm, then what you have to do, the surface zone, this surface zone, this is the zone 1, you can see here, this is the zone 1 and this is the zone 2, bottom area is zone 2. So the depth we take for zone 1, this will be only d by 2, okay, this will be only d by 2, therefore we will be taking the depth for calculating AST minimum as d by 2, that is our depth or thickness is 200 mm, so we will be taking 200 divided by 2, okay. So like this we have to take the depth, so multiplied by 200 divided by 2, okay, because it is area of surface zone, okay. So this value of AST minimum, this will be equal to 350 mm square, this is equal to 350 mm square, and it is less than this AST required, that is 670 mm square, okay, that is AST required, okay, hence okay, hence okay, hence it is okay. So this satisfies the criteria. So what we have to do now, we have to provide the steel reinforcement, okay. We have got AST is equal to 670 mm square, we have got AST is equal to 670 mm square, okay. Now what we will be doing, we will provide half of this reinforcement, that is 50% in top mesh, sorry, in inner side mesh, okay, inner side mesh, okay, 50% of this 670 will be provided on the inner side, so 50% will be equal to 670 divided by 2, and remaining 50% that will be provided on outer side of wall. So this is equal to 670 divided by 2. So if this is your wall, tank wall, if this is your tank wall, then 50%, that is half of the steel AST required will be provided like this, and half of the steel provided will be provided like this. Therefore we will be calculating the spacing, okay. So we have to calculate the spacing now, sorry. So spacing for inner side and outer side steel, okay, this spacing S is equal to, let us assume, provide 10 phi bar, okay, provide 10 phi bar HYSD bar. So spacing formula is area of 1 bar, that is pi by 4 into 10 square multiplied by 1000 divided by steel available is 670 divided by 2, so this will comes around 230 mm center to center, okay, this will be 230 mm center to center, okay. So what we will be doing, let us provide this at approximately equal to 200 mm center to center, okay. This is not necessary, you can also provide at 230 mm center to center, but I will be reducing the spacing, okay, for safety only, okay. So what we will be doing, so this spacing is for hoops, okay, hoops, because this is for hoop tension reinforcement, or this is for resisting the hoop tension. So what we will be doing, we will be providing this 10 mm 5 bars at 200 mm center to center up to a height of 0.3 meter from the top, okay. What we will be doing, we will be providing this hoop steel like this up to a height of h by 3 from the top only, okay, sorry, up to a height h by 3 from this height, okay, this will be 2h by 3 will be providing this steel reinforcement up to a height of 2h by 3 from the top. Okay, and for remaining height we will be providing in this region, we will be providing the steel reinforcement which was correlated with the bending moment. Okay, so therefore provide 10 phi bar at hoops. This will be 10 phi hoops at 200 mm center to center, 200 mm center to center, up to a height of 2h by 3 from top. Okay, and then half of the bar can be curtailed. Okay, why we will be curtailing? Because we want economy. Then 50% bars can be curtailed. Okay, so in this particular region of h by 3, this h by 3, what we will be doing? We will be providing spacing of 400 mm center to center. We will be providing this spacing of 400 mm center to center. Okay, then now what we have to do, we have to check whether the calculated stress in concrete in direct tension are within limit or it exceeds. Okay, so AST provided will be, AST provided, what we are doing, we are providing of 10 mm phi bar. Therefore AST provided will be equal to 2 into, okay, for 10 mm phi bar, pi by 4 into 10 square, okay, multiplied by 1000, and spacing we are providing is 200 mm. So AST provided, this, why the multiplier factor of 2? Because we will be providing this thing on the both the face, that is inner and outer face. So this will be equal to 785 mm square, 785 mm square. So check, next step is check stress in concrete in direct tension, okay. So formula for calculating the stress in direct tension, sigma dash Ct, this is equal to T divided by, the formula is T divided by 1000 T plus m minus 1 into AST. Just put these values. We have T is equal to 87.08 into 10 raised to power 3, just converting it into Newton, divided by 1000. Value of T is known to us, that is 200 mm, plus m is 9.33 minus 1 into AST provided. AST provided is 785. So 785. So we get this value of sigma dash Ct. This is equal to 0.42 Newton per mm square. 0.42 Newton per mm square. This value is less than sigma Ct. This value is less than sigma Ct. Sigma Ct is 1.5 Newton per mm square, and hence okay. Okay, so the stresses developed are less than the permissible stresses, and hence this particular AST is okay. Now next what we have to do, we have to design the steel reinforcement. We have to design the steel reinforcement for your bending moment. We have to design the steel reinforcement for bending moment. So next step, whatever it may be, I think step number 6 is there. So design for bending moment. Okay, we have already calculated the maximum negative maximum bending moment. Negative maximum bending moment is equal to 7.5 kilonewton meter. We have this value is already calculated. Okay, and the formula for calculating AST required is equal to m divided by, that is bending moment divided by sigma st into j into d. Okay, we have already calculated the value of j, we have already calculated the value of j, that is design constant, and d. Okay, d, this d is equal to capital, sorry, this d, this d is equal to thickness minus effective cover. Let us assume 50 mm effective cover is there, therefore 200 minus 50, this d will be equal to 150 mm. This is the effective thickness, effective depth of your wall. So this AST required, this will be equal to m is 7.5 into 10 raised to power 6 Newton mm divided by sigma st. We already know this value, that is 130 Newton per mm square. J we already calculated this as 0.86, and the value of d we have just calculated 150, so this is equal to 150. So AST required, this is equal to 448 mm square, 448 mm square, and this value of AST required, this is again greater than AST minimum, that is we already calculated AST minimum as 350 mm square. Okay, and hence okay, and hence it is okay. Let us provide for calculating the spacing, provide 8 mm phi bars at 100 mm center to center. Okay, spacing कैसे कैलकुलेट किया है, तो spacing is equal to area of 8 phi bar, that is pi by 4 into 8 square multiplied by 1000 divided by AST provided. AST provided is 448, that is equal to 112 mm. Okay, approximately we will be providing 100 mm. Okay, provide at 100 mm center to center. So this much steel will be required. This will be the vertical steel. Earlier steel which we have calculated, that was will be provided as a hoops. Okay, now we have to check whether the development length criteria is satisfied or not. Okay, so this development length criteria part, that is already covered in your RCC. Okay, so checking. Okay, now this steel, okay, that will be required to be provided up to a height of 1 meter above the 1 meter above the base. Okay, so this stirrups, sorry, not stirrup, these bars, 8 mm phi bars are provided at 100 mm center to center, 100 mm center to center on inner face, as a vertical steel reinforcement, and at the bottom face. Okay, so now we have to check for the development length. The formula for calculating development length, LD is equal to pi sigma st divided by 4 tau BD. So this is, we know the diameter of bar, that is 8 mm. Sigma st is 130 divided by 4 into tau BD. The value of tau BD is taken from clause number 26.2.1 of IS 456. There is one table on page number 42, okay, which gives the value of tau BD for Fe415 bars as 1.6. Okay, so this development length, you just check this value, because I have not opened that particular IS 456. Okay, so we get the value of development length as 163 mm. Okay, 163 mm. Therefore, as we are getting this 163 mm steel development length, therefore what we will be doing, we will curtail half of these vertical steel bar, and then rest of the bars will be continued till the top of your wall. Okay, so what we will be doing, if this is your wall, okay, half of the bars will be up to this height, that is 1 meter, and then remaining bars will be continued up to the top, okay, like this. Okay, and AST minimum, again AST minimum will be required to be provided. AST minimum will be equal to 0.35%. so this we already know the value, that is we already calculated this value as 350 mm square, 350 mm square, and spacing required for this will be 140 mm center to center. Okay, just put the value for 8 mm 5 bar and you will get the spacing required. Okay, now the last step is design of base slab. Okay, so as per general requirement of your water tank, okay, as per IS 3370, the minimum AST required shall be 0.35%. okay, minimum AST required is 0.35%, and let us assume 200 mm thick base slab. Okay, so for 0.35% steel, and we have already calculated this value for 200 mm, that is AST will be equal to 350 mm center to center. This will be provided at the bottom and top face of your base slab, and the final steel providing 8 mm 5 bars. Okay, the spacing comes out to be around 140 mm center to center again. Okay, so this is the final step, and the last step will be the drawing. Okay, we have to check the drawing. Okay, so steel will be provided like this, you can see here. Okay, vertical bars will be for resisting, these vertical bars will be for resisting the bending moment. Okay, and the main bars will be provided up to a height of 1 meter only. Okay, up to height of 1 meter vertical bar. For vertical bars, the vertical bars will be provided up to a height of 1 meter, and then 50% steel reinforcement of vertical bar will be curtailed, and remaining 50% will be provided up to top. Okay, 50% steel reinforcement will be provided up to top, and then for hoops or circular bars will be provided like this. Okay, these circular bars which are shown by these pink color dots, okay, these are for resisting the hoop tension. Okay, the hoop tension will be these steel bars will be provided closely spaced within this particular region, okay, at a spacing of 200 mm center to center, and for this remaining region or remaining part of your water tank wall, it will be provided at a spacing of 400 mm center to center. Okay, then this haunch is provided, and a steel reinforcement bar will be provided like this. This will ensure the fixed joint between your base and water tank wall. Now regarding your reinforcement of your base slab, okay, this reinforcement is provided as AST minimum, that is 0.35% of cross sectional area. Okay, the spacing will be same in horizontal like this horizontal steel at the top, again we have horizontal steel at the bottom, and then transfer steel will be there, like this. This is shown by this blue dots. Okay, this transfer steel will be there. Okay, every steel will be 0.35% of the surface cross sectional area or surface zone. Okay, so spacing will be same, that is 140 mm. Okay, so this is the final step of design of this water tank with fixed base.